In 1966, on the southeastern coast of Barbados, an extraordinary experiment began to take shape. The U.S. Army, in partnership with the Canadian government, initiated tests with one of the largest artillery guns ever built. This immense weapon was unlike anything seen before. A 36-meter-long barrel constructed by welding two 16-inch naval guns together, end to end. Into this massive barrel, technicians loaded over half a metric ton of black powder. To withstand the enormous pressure generated during firing, the barrel was fitted with heavy reinforcing rings along its length, while long, straightening rods kept it carefully aligned. Painted a bright white, the gun was immediately distinct from military artillery, which was typically cloaked in olive camouflage. This was not a weapon of war, but a scientific instrument, a space cannon designed to launch projectiles to extraordinary altitudes. In fact, it was capable of sending a payload to 180 kilometers, nearly halfway to the altitude of the International Space Station, and higher than any projectile fired from a gun before or since. To this day, it holds the record for the highest altitude projectile ever launched. The remnants of this experiment still lie rusting on the beaches of Barbados, visible to passengers taking off from runway 09 at Grantley Adams International Airport. The project behind this strange gun was called HARP, short for High Altitude Research Project. It was born out of a joint effort between McGill University in Canada, the Canadian government, and the U.S. Ballistics Research Laboratory. The immediate goal was to gather valuable data about the upper atmosphere, which in the 1960s was of immense scientific and military interest. During the same decade, the SR-71 Blackbird was making its first flights, and knowledge of atmospheric conditions at high altitudes was critical. Sounding rockets could gather such data, but they were expensive. A giant gun, capable of hurling instruments skyward at a fraction of the cost, seemed like an elegant alternative. Barbados, rather than Canada, was chosen as the site for HARP's tests for several reasons. Positioned at the easternmost edge of the Caribbean, it allowed the gun to fire eastward over the ocean, providing essentially unlimited space for debris to fall harmlessly into the sea. Its location near the equator offered a natural advantage. The faster rotational speed of the Earth that reduced the energy needed to reach orbit. Barbados also lay close to the established tracking infrastructure for Cape Canaveral launches, making it easier to monitor the flights. At the same time, the island was of particular scientific interest because it sat within the Atlantic hurricane nursery. In the early 1960s, Barbados was a poor country, heavily dependent on sugar exports, and only beginning to transition toward tourism after gaining independence from Britain. For its leaders, the chance to host a cutting-edge space launch project was irresistible. Creating a gun that could fling scientific instruments into near space demanded a careful balance of design choices. The projectiles needed to be narrow, dense, and as aerodynamically efficient as possible to overcome drag. To achieve this, HARP used saboted rounds, in which a narrow projectile was encased in lightweight supports that sealed the barrel, but fell away once the projectile exited the muzzle. The sabots were made of lightweight aluminum, reinforced with steel inserts to handle the immense pressure at the base. Plywood spacers kept the projectile aligned in the barrel, while soft polyethylene provided a gas-tight seal without damaging the barrel's interior. This approach maximized the ballistic coefficient of the projectiles, ensuring they traveled as far and fast as possible. The ultimate altitude reached depended entirely on muzzle velocity. Once the projectile left the barrel, only atmospheric drag acted upon it, steadily draining away its energy. Achieving higher velocity meant releasing more energy from the propellant, but doing so without damaging the barrel required precise control over internal pressure. To study these dynamics, HARP employed piezoelectric crystal sensors, which transformed mechanical stress into measurable electric signals. These sensors allowed researchers to monitor pressure along the barrel in real time, unlike older methods that only indicated maximum pressure. The goal was to maximize the total energy imparted to the projectile without exceeding safe pressure limits. At first, HARP used massive 50-kilogram bags of black powder stacked behind the projectile. Each bag contained ignition charges sewn into its base, designed to ignite sequentially as the flame front advanced from the primer. But early tests revealed problems. Pressure curves measured by the sensors were much higher than expected, and muzzle velocities came in lower. Inspecting the polyethylene discs from the sabots, scientists found grains of unburnt powder embedded in the plastic. They theorized that the initial ignition created a pressure wave that compressed the powder bags, driving them forward before the flame front could properly ignite them. When the bags slammed into the projectile, they generated localized high-pressure zones that wasted energy and even damaged the sabots. To address this, researchers experimented with an ingenious test device called the HARP flyer, a shorter instrumented barrel mounted on rails that recoiled dramatically with each shot. Here they tried new methods of arranging propellant. By inserting lightweight wooden spaces between the powder bags, they prevented the column from being driven forward prematurely and allowed hot gases to ignite later charges more effectively. Pressure curves improved, though the issue was not entirely solved until electrically fired squibs were introduced, igniting all bags simultaneously. The projectiles themselves took many forms, depending on their scientific payloads. One remarkable design carried trimetal aluminum, a chemical that reacted with oxygen in the upper atmosphere to create glowing clouds visible from the ground. These luminescent traces made it possible to study wind shear at altitudes that conventional balloons and aircraft could never reach. Compared to sounding rockets, the gun provided a far cheaper and more reliable means of conducting such experiments, which was exactly why the U.S. Army remained interested. But the Canadian leadership, particularly engineer Gerald Bull, had even more ambitious goals. They envisioned the gun as the foundation for a low-cost satellite launch system. To achieve orbit, however, would require more than brute force. The projectile had to survive immense acceleration, ignite its own rocket stages after leaving the barrel, and gradually build up horizontal velocity. Bull and his team designed the Martlet series of rockets for this purpose. The Martlet 3E, for example, was a fiberglass-cased solid rocket with flip-out fins, capable of carrying a 25-kilogram payload to 450 kilometers, higher than the orbit of the ISS, though still lacking the lateral velocity needed for orbit. The ultimate ambition was the Martlet 4, a multi-stage orbital launch system fired directly from the giant gun. To make this feasible, guidance systems, staging mechanisms, and propellant casings had to survive launch accelerations of thousands of Gs. Experiments in Canada included horizontal firings over frozen lakes, where test rockets could be recovered intact after skidding across the snow. Despite promising progress, the project ran into insurmountable bureaucratic obstacles. The U.S. Army prioritized upper atmosphere research, while McGill University and the Canadian government hoped for a path to space launch capability. Reconciling these conflicting goals proved impossible, and when the funding agreement expired in mid-1967, Project HARP was abruptly terminated. Gerald Bull, left without support, sought other patrons. His career took a dark turn as he became involved in international arms deals, violating embargoes and eventually collaborating with Saddam Hussein on Project Babylon, an ill-conceived supergun intended to bombard Israel. Before it could be completed, Bull was assassinated outside his Brussels home in 1990, almost certainly by agents of Mossad. Though HARP ended in failure, its legacy lived on in subsequent experiments. In the 1990s, Project Sharp in California developed a light gas gun capable of accelerating projectiles to 7 kilometers per second using hydrogen. More recently, private ventures such as Spin Launch have explored entirely new forms of kinetic launch, using massive centrifuges to hurl payloads into the sky. These efforts build on the same core insight that inspired HARP, that alternative launch systems might one day dramatically reduce the cost of reaching space. The white-painted cannon on a quiet beach in Barbados remains a rusting monument to that vision, a reminder of the strange chapter in history when scientists turned a naval gun skyward and tried to blast their way into space.